a portion of the graph of the function k of x is shown to the right, and they give us a bunch of information about k of x. For example, from -1 to 1, this part of the function is a quarter circle, so it's 1/4 of a circle. And from 1 to 4, the function is piecewise linear, so we have a line from 1 to 3, and we have another line from 3 to 4. So you have two pieces of the lines. And the only interval from 4 to 6, we see that we actually have a parabola. So it's this parabola, and we see it right here. And they even tell us the area underneath the parabola is 8/3. And given this, I want to take a look at part B of the problem, which asks us to graph the continuous antiderivative of k of x with k of 1 is 0. And let's quickly review what antiderivative is. So when they say this capital K of x is the antiderivative of little k of x, all we are saying here is that when we differentiate this capital K, so when I take the derivative of capital K, we get little k of x. As you're preparing for exam 1, you might have encountered problems where you're given a function and then you have to differentiate this function and sketch the derivative. Now the situation is reversed. Rather than differentiating this function, we want to figure out what function do we differentiate such that the derivative is this function. So that's what we're trying to do here. And to start with, I want to point out there's one ambiguity when it comes to anti-differentiation. And that's that there is some constant of integration that's associated to it. So if you know, for example, that maybe little k of x, I mean, this is not the case, but suppose for the moment, the little k of x was 5. So what would be capital K of x in that case? Well, if we know when we differentiate this function, we got 5, then that's telling us that our function must have been, say, like 5x plus some c. Right? It's a line with slope 5. So when I differentiate this, then I get 5. Of course, the problem here is that we have this constant of integration, and we don't know what this is. Like for all we know, so if this is the xy plane, our line can be this line with slope equals to 5. That's one possibility for capital K of x. But it can also be, say, like 5x plus 2, and maybe our line actually looks like this. It can be 5x minus 1. Maybe our line looks like this. So we don't know how much the vertically shifted up or down. So this might get you a little confused because we are trying to sketch the antiderivative, but since we have plus c, we don't know how much to shift it up and down. So how is it possible for us to graph it? Well, that's the reason they give us some additional information here. So the very first thing when you're approaching problem like this is to look at this extra condition that's actually specifying some point. So here they are telling us k of 1 is 0. And what kind of information is this? Well, for example, if we're dealing with this family of lines and you're trying to figure out which line do we actually care about, well, what they're telling us here is that they're telling us maybe the line goes through some point. So they're telling us that there is actually a point that the line goes through, and now, once I tell you that information, now you know it's this line, right? Because, for example, this line cannot be it because it's not going through the point that I'm telling you that the antiderivative is going through. So that's what this key information is telling us. This k of 1 is 0. So this should be the very first thing that you start with. I guess for those of you curious, it deserves to be pointed out the fact that they're asking us to graph the continuous antiderivative actually matters a lot. But I mean, don't worry about it too much. Really, what you should remember here is that since capital K of x should be continuous, if you find yourself graphing something that's not continuous, for example, if you find yourself graphing something like this, where you have a jump, or maybe you have an asymptote or something like that, then you know you're doing it wrong. So they're asking you for a continuous function. And now there's actually one more thing I want to say before we officially start. And it's one important fact between function and derivative that you may remember from preparing for exam 2, and it's the following relationship. So again, remember that you can think of this as being the function and this as being the antiderivative, but another way to think about it is to think of this as being the function and this as being the derivative, right? Because when I differentiate this, you know you're getting this function. So a lot of the things we know from exam 2 is going to be true in this problem. Like for example, so when is our function going to be increasing? Or how can I check whether it's decreasing? Well, capital K of x is going to be increasing when the derivative, the little k of x, is positive, right? And it's going to be decreasing when the derivative, little k of x, is negative. So for example, here, little k of x is positive, it's above the x-axis here. So you know this capital K should be increasing on this interval. And we also know that we can figure out the concavity of a function by looking at whether the derivative is increasing or decreasing. Namely, we can figure out whether it's concave up or concave down by looking at the derivative and looking at whether it's increasing or decreasing. We know when our function is concave up, the derivative should be increasing, and concave down should correspond to the derivative being decreasing. So that's the key information I want you to remember. So that's one key ingredient. The second key ingredient that we'll use is the following. It's that when I integrate from a to b of this little k of x, dx, then what does this get you? Well, by fundamental theorem of calculus, this gets you the change in antiderivative. So antiderivative of little k, which is exactly capital K of x, from a to b. You might have also commonly seen it being written as capital K of b minus a capital K of a. That's exactly saying how much does capital K change from a to b. And this key formula and the fact that this can be thought of as, say, signed area under the curve of little k is going to become very useful in graphing this capital K. Okay, so now let's actually get started on graphing this. So again, the very first thing you should do is look at this initial condition, which you absolutely need to be able to graph this, and plot that point. So we know k of 1 is 0. So let's plot a point right here. And how do we proceed? Well, let me make sure that we understand what we're trying to do. We want to make sure whatever the value that we plot at x equals to -1, 1, 3, 4, and 6 better be pretty accurate. And this capital K of x, we want to make sure we indicate where it's increasing, decreasing, and constant. And the concavity and the inflection point, we should keep in mind of that as well. I guess something to point out, where k of x is and is not differentiable, if you really graph everything roughly correctly following these three parts, then I think the first part is usually going to follow suit. And this inflection point, as long as we get the concavity right, you're probably going to get the inflection point correct as well. So really, we should focus the most on the value of k of x, increasing, decreasing, and the concavity. Those are really the key parts that I want to look at for now. So what do we do? Well, we know what's happening exactly at 1. So why don't we start by looking at what's happening between -1 and 1? So why don't we go up and see what's happening here? Well, from -1 to 1, what do we have here? Well, we see that our little k of x is positive, and we also see that it's decreasing. And now let's think about what this means. Well, we know, again, thinking of this as being the function and little k of x as being the derivative, we know when the derivative is positive, our function was increasing. And since our derivative here is decreasing, we know our function should be concave down. So what we know for sure is that for this capital K of x, from -1 to 1, so in this interval right here, from -1 to 1 here, we know our capital K should be increasing and concave down. So again, this positive corresponds to increasing, decreasing corresponds to concave down here. Now, what does a function that's increasing and concave down look like? Well, concave down means you're making some sort of frowny face and you're increasing. So you're going to look something like this. You're making a frowny face, so it's concave down, and you're going up, so it's increasing. So we know we should get a graph like this from -1 to 1. But now here's the key question. So we know we're going up from -1 to 1, but how much are we increasing by? So that's another key question. And how we find it is by looking at the signed area under the curve. So we know when I take the area of this little k of x from a to b, then that gets you how much antiderivative is changing from a to b. So all we have to do now is find the area right here. So once we find the area right here, that's going to tell you how much we're increasing by in capital K. And what is the area of this? Well, we know from the problem statement that this is a quarter circle. So this is 1/4 of a circle. And here the radius, if you look at it, is 2. So if the radius is 2, the area of the circle is 4 pi. But you only care about 1/4 of it. So here the area of this part is exactly pi. So what does that tell you? That tells you that from -1 to 1, we're going up like this by pi. And since after going up by pi, our y value was 0, so we better start at -3.14 and -1. So we better start at -pi-ish, and then we know we're going up, we know we're going all the way up to 0 y value. And I guess something to point out is they don't really tell us to pay too much attention to what's happening at x equals to 0. So when x equals to 0, maybe we don't have to be so precise. So I think this is good enough for now. So let's move on to the next part. So what's happening, for example, from 1 to 3? So what's happening here? Well, we see here that the little k is negative, which means capital K better be decreasing here. And we see that little k is increasing, which means our capital K should be concave up. So we know, just to recap, since this thing is negative and increasing, we know our capital K better be decreasing and concave up. And if you're decreasing and concave up, what do you look like? Well, concave up means you're making a smiley face, but you're decreasing. So you're going to look something like this. You're making a smiley face while going down. But now the question is, how much are you going down by? And that, again, we look at the area under the curve up to sine, I guess. So here, the area that we care about is this area. And it's a triangle where the base is 2 and the height is also 2. So 2 times 2 divided by 2, area here is 2. But again, this area is below the x-axis. We know our capital K is decreasing. So we know we're going down by 2 while making a shape like this. So let's go down by 2 from 1 to 3. So that's gonna get us at -2. And we have our function looking something like this. Now what's happening next? Well, let's look at what's happening here. Now, from 3 to 4, well, here we see our little k is positive and increasing. So since our little k is positive and increasing, what do you know about capital K? Well, capital K better be increasing and concave up. So if you're making a smiley face while increasing, then you know you're looking something like this. So now the question is, how much are you increasing by? And this you do so, you figure out by looking at the area under the curve. So what's the area of this triangle? Well, the base is 1 and the height is 2. So the area here is 1 times 2 over 2. So area here is just 1. So you know you're going up by 1 while making this smiley face from 3 to 4 here. So let's throw that out. You're going up by 1. So you want to plot a point here and you're making this sort of concavity increasing up. Now what's happening next? What is happening next is that from 4 to 6, we see that we're positive but decreasing for little k. So what's that telling you about capital K? Well, that's telling us, to finish, we already know increasing and concave down looks exactly like this. So now the question is, how much are we increasing by? Well, we increase by area of this region, which they tell us is 8/3. So you want to go up by 8/3. So if I start at -1, so if I start a y value of -1, and you go up by 8/3, then you should arrive at 5/3, which is like, what is it? It's like 1 2/3. That's like 1.6 repeating. So we know by 6, you want to get to like 1.6 repeating. So you know you're somewhere here. And what do we know? We know you're making this sort of shape. So when I draw it, here we go. We got what we wanted. I guess maybe you are curious on whether we got this, where k of x is or is not differentiable condition right. And we see that we indeed have, because for example, we see here that capital K is not differentiable. And why is capital K not differentiable there? Well, that exactly corresponds to the fact that when I try differentiating it and get the derivative of little k, the little k is undefined. We see that we have a hole here in both cases at x equals to 1. So little k is undefined. So capital K should not be differentiable. And since we did everything roughly correctly, we got that for free in some sense. Whereas, for example, I guess you want to make sure that at this point, your function, your capital K looks differentiable, because when I differentiate it, I get this value, which is obviously well defined. It's the derivative exists, so it should be differentiable. So I guess maybe if you want to make this even better of a graph, you want to maybe smooth it out so it looks like there's less of a sharp turn. So I guess that's one thing you can improve on, but this is roughly how you want to approach the question.